So recursion has some benefits and some drawbacks. In terms of disadvantages, it can be, at least at first, quite difficult to solve problems or to think recursively. There's definitely a learning curve when it comes to recursion. A lot of people, when they first face recursion, think of it as sort of a reverse version of the iterative repetition we already know. And another disadvantage of recursion is that function calls require overhead. If we have too many recursive calls, our programs will crash, as we've seen. But even if we keep our recursion depth in check, there's still some small overhead with every function call. We have to set up a new scope, add an instance onto the call stack, etc., etc. So some small amounts of time and space are wasted with each function call. These are negligibly small, but still more than in a standard while or for loop. So iteration is oftentimes a faster way to solve the problem, and oftentimes requires less memory as well. The advantage of recursion, though, is that it's oftentimes easier to implement a solution to a problem, at least once your thinking reorients to solving problems recursively. So with some pattern recognition, you might start to see problems that have obvious base cases and simple reduction strategies, which makes coding them in a recursive fashion very easy. For example, once we learn that there's a recursive definition for the factorial problem, it is very easy to solve that recursively. Recursion is also sometimes very well suited to certain problems, so the solution is expressed quite naturally, where an iterative solution to those problems might actually be quite difficult to conceive of. So for example, traversing a file system, or really any other tree-structured data, if we can create a branching recursive pattern, is easier to solve than trying to create a single loop that branches in multiple directions. As an example of branching recursion, let's consider the Fibonacci sequence. So the Fibonacci sequence is a sequence of numbers where each number is the sum of the two numbers before it. So we have 0 and 1 are the first two numbers, and then the next number is the sum of those two numbers. So 0 plus 1 gives us 1, and then 1 plus 1 gives us 2, and then 1 plus 2 gives us 3, 2 plus 3 gives us 5, 3 plus 5 gives us 8, then 13, then 21, then 34, 55, 89, 144, etc. This sequence of numbers ends up being quite important in nature. So the ratio of one Fibonacci number to the next approaches what's known as the golden ratio, phi, which is about 1.618 or so. You might have seen images of a golden spiral, which is a spiral constructed based on this ratio, which demonstrate this Fibonacci sequence. You can also see the golden spiral show up in places like spiral galaxies or in hurricanes, or even flowers and pine cones. They typically have a Fibonacci number of petals or spirals, and the angle between those petals or spirals is known as the golden angle, which is a function of phi. Even the human body contains phi in the ratio between various parts of your body. So between, for example, the different parts of your finger, or the ratio of the size of your hand to the length of your arm. Supposedly, even the size of DNA bears markers of this golden ratio. So it applies to a lot of different things, but we're using it here because the sequence itself has a very concise and recursive definition. So the program we'll create, according to this program task, is to write a recursive function fib_n that returns the nth Fibonacci number. So we're just going to calculate the numbers of the Fibonacci sequence itself. So in terms of a mathematical definition, we can say the Fibonacci sequence is defined by these three equations. The first two equations would be our base cases, so there's no recursion in there. So we say fib of 0 is 0 and fib of 1 is 1. For all other numbers, we calculate the fib of that number by finding the fib of the two previous numbers and summing them. As an example, if I wanted to compute the fifth Fibonacci number, so I'd say fib of 4, because zero-based indexing, in order to calculate that, I need to know the fib of 3 and the fib of 2. Now, in order to know the fib of 3, I have to know the fib of 2 and the fib of 1. And in order to know the fib of 2, I have to know the fib of 1 and the fib of 0. And similarly over here, in order to know this fib of 2, I also have to know the fib of 1 and the fib of 0. So there's a bit of repetition in this tree. Okay, so each one of these values is a function call. So our user wanting the fib of 4 will just type fib of 4, but then the definition of that function will have to calculate or call the fib of 3 and the fib of 2. Then to calculate the fib of 3, we'll have to call the fib of 2 and the fib of 1. Get the fib of 2, we'll have to call the fib of 1 and the fib of 0, both of which are base cases, so it can do that trivially, and return those values, sum them up to get the fib of 2. And then it sums that with the fib of 1 to give us the fib of 3. And then it calls fib of 2, getting fib of 1 and 0 from that, summing all that up to give us fib of 4. So we'll return to this tree in a moment, but let's see if we can't write our code now given this simple Fibonacci definition. So comment out this code. We'll come down here and say def fib of n. And this computes the nth Fibonacci number. Oh, I spelled that wrong. Fibonacci number. And I will say recursively. Okay. Now the definition of a Fibonacci number is already described recursively as we've seen. So we have two base cases in this case. So we'll say if n is equal to 0, that's one base case, in which case we'll return 0. And if it's not that, we'll ask, is it equal to 1? In which case we'll return 1, which is another base case. And lastly, if it's neither of our base cases, then we'll compute the recursive case. So we'll say return the fib of n minus 1 plus the fib of n minus 2. And this is our recursive case. So note the Python implementation for our Fibonacci function is almost exactly the same thing as the mathematical definition, which makes it very natural to express in code using recursion, whereas solving this with iteration, that is to say a loop, wouldn't be as obvious, or may not be as obvious to you. In fact, as a homework problem, I challenge you to attempt to implement this Fibonacci function without using recursion. So let's test this out. I'm just going to save, and I'm going to do python-i recursion.py. So now we can ask some questions. What is the fib of 0? And that gives us 0, our base case. What's the fib of 1? And that's 1, our other base case. This is convenient. Let's make some more space here. Convenient, our code works so far. What's the fib of 2? It should be those two things added together. 1 plus 1. And if we keep going up this line, we'll see, let's keep adding these numbers. But let's jump ahead a little. What's the fib of 10? The 10th Fibonacci number is 55. I guess that's the 11th Fibonacci number. And what about the fib of 50? Well, as you can see, it's very slow. And while this tries to figure this out, let's see if I can't explain why it's so slow before the problem gets solved. So here's our Fibonacci tree for fib 4, which had to compute fib of 3 once, and had to compute fib of 2 twice, and notice we had to compute fib of 1 3 times. Now if I were to compute instead of fib 4, the fib of 5, so say fib of 5, what's that going to do to our tree? Tab everything over here. So the fib of 5 has to call the fib of 4, so notice that's that entire tree that we already had written, and then it has to add that to the fib of 3, which in order to calculate the fib of 3 is all of this stuff. Which let me just indent so I can read. Like that. So notice our tree almost doubled, by going up a single value. In fact, the complexity for this Fibonacci code is roughly order 2 to the n. That's not n squared, it's 2 to the n. It's the reverse of n squared. What that means is, if n goes up by 1, we have to double the amount of work we do. If n goes up by 2, that's 4 times as much work we're doing. If n goes up by 3, that's 8 times as much work. Okay. And it's actually not 2 to the n, it's phi to the n, but 2 to the n is an easy to see upper bound because every time we add 1, we're effectively doubling this tree, right? We had this old tree was there before, we added 1 to it, and this tree is not going to be as big, but it's almost as big as the other tree that we have there. Fib 3 is 1 step smaller than fib 4. So it's an upper bound of 2 to the n, but it's actually phi to the n, which is 1.618 to the n. So while this solution is very easy to code, it has a very expensive runtime. Now I said I'm going to leave the iterative Fibonacci code as a homework problem, but if you can solve it, it should be able to run in order n, which means if we add 1 to the size of n, we only have to do 1 extra step in our code. So what this demonstrates, and note it still hasn't finished running, what this demonstrates is that just because we can solve something with recursion doesn't mean we should. So even though sometimes these problems are very natural to be solved with recursion, it's an expensive approach at times, particularly when we have this exponential branching happening. Okay, now this is going to run, I believe, for several hours, so we're not going to wait it out, but we don't have to stop it. In VS Code, we can actually just create a new terminal. And that just has 2 terminals here, so we can go back to the old one and we can check on it later. But for now, we'll start with a fresh screen and let's do some more practice problems so we can learn how to use recursion to solve problems involving lists. So as an example, let's see if we can't solve the problem of summing a list. So we have a list of numbers and we want to sum up all the values in that list of numbers. Now again, we could do this using iteration, but we're learning about recursion, so let's solve this simple problem using recursion. So we'll say def sum list. We're just going to sum up a list. So we'll give it a parameter called list, and then we'll fill in this code with some recursion. So I'll just add a comment. This sums a given list recursively. In terms of design, what would be our base case? So think to yourself, what is an instance of our input that we can solve trivially? What kind of list can we sum up in a single step or without doing any work at all? So we have a list of numbers and we want to find the sum of all those numbers. What's a very easy instance of that problem? Well, the easiest instance of that problem would be an empty list. If there are no items in that list, then we know the sum of those items has to be 0 because that's how numbers work. So our base case is if our list, so if the len of our list is 0. Or you could also ask, is our list the empty list? So if the len of our list is 0, in that case, we know the sum of all the values in that list is 0. Then our recursive case would be to call this function, but we need to put a step in there so that we can reduce the size of the problem. So what would be one step of summing all the values in a list? Well, one step would be summing one of those values, or taking one of those values and adding it to our sum. Now in this case, we don't have a running sum variable because we don't have a loop. Notice we have many different instances of this function, so we can't just have one variable sitting outside of all those function calls that's accumulating values. I mean, we could use global variables, but that's very bad design, so we won't do that. Instead, what we'll do is we'll call this function to sum most of our list, and then we'll add the current value onto that sum. So we'll take one item out of the list, we'll call this function to sum what remains of that list, so everything but the first item. Then when it gives us back a result, which is the sum of the tail of our list, then we'll take the first item from our list and add it onto that sum. Which is to say, we'll say the current value, so list at 0, plus the result of calling sum list on the rest of our list. So how do we get the rest of our list? Well, we can take the existing list and we can just slice it. So I'll say from 1 to the end. Notice this isn't going to destroy our input list. It's not going to mutate anything. This is going to take a copy of what's called the tail of our list. So everything except the first item in our list. Then we'll take that first item, sometimes known as the head of our list, and add it on to the result of summing the tail. And that gives us the result of summing the entire list. So we'll say return all of that. Note that we can't do this in a single problem either. This is a recursive problem. If there's 100 items, we've taken one of them off and said sum the remaining 99 items, which will come back to this step and take the next one off and say sum the remaining 98, etc., etc., etc. We'll be building up the call stack, and each one of those calls will be waiting for a return. And as soon as we get to the base case, that'll return 0. So the first time this value returns will be 0, 0 plus something in our list, which will be the last item in our list. And then the item before that, and then the item before that, and then the item before that, until eventually we get to the very first time called sum list. We'll add on the very first item in our list, and that will be the sum of the entire list. Just to point out, the plus sign here represents addition, not concatenation, because list 0, assuming our list is all numbers, is going to be a number, and sum list here is going to be the result of calling our function, which is going to be either a 0 or the result of adding some number to that 0. Okay, let's try this out. So I'll say sum a given list, we'll print it so we can see what happens, and the value of that list, let's just make something we can count in our heads, 1, 3, 5, and 7. Should give us 16. And we don't need interactive Python, we're just going to run it once. And we get 16. We could do this with other lists to make sure it works more robustly, but hopefully you get the idea here. Now we can also use this same idea to implement any traversal with recursion. So for example, if we wanted to do a linear search with recursion, instead of adding each element, so instead of summing up all the values, we would check each element to see if this is our target item. And that would be our base case. If we found the target item, we return true. If our list is empty, we return false. In all other cases, we shrink the list and check the first item. Let's try another example here, a recursive filtering function. So we'll say, comment this one out. We'll say def remove odds of some list. So I believe we saw this exact example with iteration when we were first learning about loops, but let's see if we can solve it with recursion as well. So to describe this function, we'll say this filters all of the odd numbers from an input list of integers. Okay, so again, what's the base case for this problem? What's an instance of a list that's passed into our function that we can know that there aren't any odd numbers in that list without doing any work? Well, you'll come to find when doing recursion with lists, very often the base case is that very simple case of an empty list. How do we handle the empty list? Now how do we handle one item in the list? And then how do we handle two items in the list? So our base case is usually when the list is empty. So in this case, if our list is empty, then it has no odd numbers, so we can just return the list as it was given. So if list is the empty list, it's another way of saying if len of the list equals 0, then we will return the empty list. Or if we want, we can say return list, it means the same thing. Okay, if that's not the case, then we're not at our base case, so there are some numbers in our list. So now we need to solve one instance or one step of the problem and recurse on a smaller instance of that problem. So just like with our previous example, the smaller instance of the problem will be removing one value and calling the same function on the tail of our list. Ultimately, the recursive step will say something like remove odds from list from 1 to the end. Just like it did before with our sum list, we call the function on the tail of the list. Now we need to do something with the head of that list, the first item. In this case, we want to determine should we remove it or not. So we take the first item out of our list. That's list at 0. And we want to determine should this be in the list or shouldn't it. Now if we're removing all of the odd values, that means we need to first determine is this number an even number or an odd number. So we'll say if list at 0 mod 2 equals, I'll say 1. So in this case, the first item in the list is odd, in which case we can just say we don't want that number. We want to remove all the odd numbers. So we'll return the result of removing the odd numbers from the tail of the list. So because our first item, list at 0, was odd, we can just discard it. The result of filtering the list that has an odd number at the front is the same as the result of filtering the list that doesn't have that number at all. Right? Because it's filtering that number out plus filtering everything else. So in this recursive case, we're filtering that number by not doing anything with it, by just discarding it. Now, in the case that it is not an odd number, we still need to return something, and we still need to do our recursive case, but we want to keep the value that we're looking at. So to keep the value that we're looking at, we take the result of filtering our tail, so we now have a filtered tail, and now we have the first item in our hands, and we're saying this is an even number. I want to attach this to the thing that I'm returning. So if this tail, the result of calling remove odds is all even numbers, and list at 0 is a single even number, then we want to bring those two things together. So there's a few ways we could do that. We could do an insert or something. Concatenate works just as well here, so I'm going to say join these two things together, but in order to do a concatenation, we have to have two lists. Remove odds will return a list, but this is just an element, so we'll wrap it in a list so it can be concatenated. And the result of concatenating this element plus the filtered tail is the entire list filtered. I'm going to run through this, but it might actually benefit us to print out the value of the list each time. So this is going to be a little debugging line here, even though we don't need to debug, but just to help us understand. And let's print the result of remove odds on a given list that has a bunch of both. We'll do 1, 2, 3, 4, 5, 6, 7, 8. Save and run our code. So the print statement here is what we're seeing for the most part. That's all of these. And then the result is that last line, 2, 4, 8. So our code worked. That's good. Walking through what we're seeing, we enter this function call the first time with the entire list. Say 1, 2, 3, 4, 5, 6, 7, 8. That's not our end state, so it checks the first value, and in either case, it's going to call remove odds with the tail of the list. So the next time it prints out, we see the tail of the list, and then the tail of the list, and then the tail of the list. So let's consider one of these examples. So let's say, for example, the call for 8. So we print out the current list is the list with the value 8. That's not our base case. So we check the first item. It's not odd. So we come down to this step here. That step here says call remove odds with the tail of the list, which is this empty list. So it goes back up, prints that out for us, and then returns the empty list. So this step here returns the empty list. We pass in an empty list, we get an empty list back. And the value we took off of our list was the number 8. So we wrap that in square brackets to call it a list with the value 8 so that we can concatenate the two things together. A list with one item plus a list with no items just gives us our original list back. So we return the list with the value 8. That would return to the call where we had 7 and 8 as our input list. So that, because 7 is an odd number, would have hit this case here. So remove odds returns the list with 8 in it. But because our first value is a 7, it's an odd number, we don't concatenate it, so we're just returning what comes from the subsequent recursive call. So we're returning the list 8. So that goes back up to the line where we had a 6 at the front of our list, which would have been called from here, and because 6 is even, we concatenate that onto the front of the list, etc., 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 all the way back to the front of our loop, at which point we return the final result with just the even numbers. So as we're building up the call stack, we start with a full list, and as we're building up the call stack, we're shrinking our problem down and down and down until eventually it hits that base case. And once it hits the base case, notice that's when all the actual work starts taking place. So for all of these function calls, all 8 of these are still sitting on the call stack saying, I'm going to tell you what my answer is as soon as the recursive call tells me what its answer is. As soon as I get that recursive call, I'll either add the current value if it's even, or not add the current value, and in either case, return the result of that. That brings us back up the tree, adding in these values as we go. So we start with the empty list, we add an 8, we add a 6, we add a 4, we add a 2, and then we have our result list. So note in this situation we have 2 recursive cases, one for being even and one for being odd, and in both of those cases we're shrinking towards the base case. And I just wanted to revisit our friend Fibonacci here. We left Fib50 running, and I wanted to point out that it is still running. And this is despite the fact that the amount of time spent recording these videos is considerably larger than the actual runtime of these videos. So Fib50 is a very large number. And in fact, you don't have to take my word for that. Let's just quickly do a calculation here. Open up Python. So I said the complexity of our Fibonacci algorithm was upper bounded by 2 to the n. So if n is 50, we could say 2 to the 50 is a fairly large number. So this number represents the upper bound on the total number of function calls that we'll have to create in order to do this Fibonacci sequence. Now I mentioned it's not actually 2 to the n, it's actually phi to the n if we look closer, so 1.618 to the n. So a slightly smaller number, but still very large. And that's, by comparison, we did fib to the 10 in a matter of seconds. That's because that's only 100 steps. So the calculation for our Fibonacci sequence using recursion is an exponential growth. So for each small increment in the size of our problem, we have to multiply the amount of work we're doing to solve that problem. And that's it for this video. Now on to the next one.